The first eigenvector is going to be the first column. The second eigenvector will be the second column. But also, I will normalize it. How to get a unit vector from a vector? This is related to vectors. To get a unit vector from a vector, you will have to divide the components of each vector on the sum of the squares of its components. Can you say that once more? I will have to divide each vector on its magnitude. What's the magnitude of a vector? The square root of the sum of squares of its components. So let's get the magnitude of the first vector. Do it with me. Negative 1 to the power of 2.
1.
2 to the power of 2.
4.
Their sum is
5.
under square root will be
4.
root 5. Exactly the similar steps for the second vector. So now I'm dividing each vector, but of course it's not going to make a difference because you have the basis of this vector. But that's an answer came into your mind. You wanted to ask me. Do you remember once we are evaluating the first vector? We were trying to evaluate the first vector and we chose number 2 in order to make those integers. صح? What if I choose 4? What if I choose 5? What if I left it the way it is? The vectors will be different, am I right? The components I mean. So this case will make them an issue. So it will make no difference, am I right? If you add 5, 6, 7, 2, 4, whatever, you normalize, you get the unit vector of this vector. So how to get a unit vector from any vector? Simply divide the components of the vector on its magnitude. What's the magnitude of a vector? The square root of the sum of the squares of its components. Yes, Ziad, it is not a must to have these two guys equal to each other. Here it's just by chance. Okay? But it's not a general case. I can make maybe in another numbers, if I choose this guy to be 4, for example, u12 is equal to 4, then the magnitude will be different. Am I right? So it's just a coincidence. Are you with me? Now I have the B matrix in front of you. That's the B matrix. That's the U matrix. Yes, yes. Do you remember the first slide when I show you A matrix and the diagonal matrix? Yeah? Okay, no, not the inverse. Do you remember the first slide when I show you the diagonal matrix and the similar matrix? Now I can get the similarity. But before doing so, there is a remarkable advantage for this matrix. Which is, this matrix, it's an orthogonal matrix. Once more, what's the orthogonal matrices? Are those type of matrices, once you get the transpose, it's the inverse. So this matrix is 0. Get the transpose, which is? So simply, I will make the first column and the first row.
Yeah.
Okay, and the second column is going to be the second row. So now, once you get the transpose of these two matrices, if you multiply them together, that's the check. U2 times U. So actually, this matrix, it's the inverse, the C matrix. For this case, let's multiply them together. If you want to check, multiply these two guys together, the first row by the second row. Okay? So if you multiply them, you will have a unit matrix. Let's try it. Negative 1 over 5 times negative 1 over 5, it will be 1 over 5. Negative 2 over root 5 times 2 over root 5 is going to be 4 over 5. 1 over 5 plus 4 over 5 is going to be 1. Here we go. Those are the numbers of the multiplication. You will end up adding 5 over 5. If you multiply the first row by the second row, you will have a 0. This is going to be a negative 2, that's supposed to 2, it's not 0. So now I have a unit matrix. So it's really happening. The transpose in the inverse. So that's the orthogonal matrices. Let's go to the second step. What's that mean? If I got the inverse, u minus 1 times A times U, I will get a diagonal matrix, which is a similar matrix for A. But this matrix is a beautiful piece. Let's do it. This is the transpose, the inverse yani. This is the A matrix. That's the main U matrix. This is the one that I wrote from the eigenvectors. If you multiply them together, multiply these two guys together, then the result will be multiplied by this matrix. You will end up having this case. Once you do the multiplication ziyad, you will have this guy. Once you simplify it, voila, that's the diagonal matrix. It's a diagonal matrix with a huge advantage. What's the huge advantage in this matter? This is 10. And that's an answer once more for you. If you replace these two guys, 10 and 5, then these two columns will be replaced. Alright? Then once you do everything, it will be exactly similar. But at the end, you will have a diagonal matrix. The first element will be
5.
10. And the second element will be 10. So if you change from the first, you will get the result with the change unit. The steps are systematic. They close each other very successfully. Are we okay? It's a very simple matter. I want you to redo this problem. Actually, I've built 3 similar problems for you. 3 of them. That's the first. Okay, let's remark also our lecture didn't end. We have a lot of things to do. So wait. Now, keep focusing. Ziyad, keep focusing. Look to this problem, which is exactly similar to the previous one. But I will change it. The matrix. This is the new matrix. I need to evaluate exactly the same. Eigenvalues, eigenvectors, normalized matrix, doing the checks and reaching the diagonal matrix, which is a similar matrix to the first, okay, but in a diagonal form. Let's do it together. I'm not going to go through the steps literally because it's already okay. Once more. So the first step will be getting the determinant, which is going to be 1 minus e to negative 5 therefore 1 minus e. Trying to expand it. It's going to be 1 minus e squared minus 3 5 equal to 0. It's a quadratic equation. Trying to expand it. And factorize it. I have these two guys. Eta minus 6 times eta plus 4. The result is 6 and negative 4. Okay? Do you remember what's the difference between this matrix and the previous one? The sign of the eigenvalues. The sign of the eigenvalues here are different. Am I right? But the sign of the eigenvalues in the previous problem, they had the same sign. They were positive. Am I right? Yeah. By the idea, let's do a quick definition. We will catch it down the road. Once the eigenvalues are exactly with the same sign, we call it a positive definite matrix. A positive definite matrix. If they have different signs, we call it an indefinite quadratic matrix or a matrix. The deficiency of a matrix, it's related to the eigenvalues. There is another ways, of course, but this is the simplest and the most purest one. Getting the values, the results of the eigenvalues, I will look to this line. If they are positive, then I can classify this matrix to be positive definite. What if I've solved this problem and I have negative 5, negative 10? It will be called, by logic, negative definite. Can you do it once more? If you have the eigenvalues positive, it's going to be called positive definite. If the eigenvalues, both of them have the same sign, but it's negative, I will call it negative But if they have different signs, I will call it indefinite. So this case, it's an indefinite matrix. Nothing. It's just a definition for the time being. So the system is really very simple. Now I will have to use this system of equations in order to find the corresponding eigenvalues. Vectors. So I will do exactly the same. This is for eta equal to 6, and I will start substituting, guys, which is going to be y minus 6, y minus 5, y minus 6. I will end up having this case. If you remark, you have two identical or there is a relation. So multiplying the negative and the adding, you will have your infinite number of solutions. Am I right? And the first component is equal to the negative of the second component. Are we right?
Yeah.
Am I right? So once more, yes, negative 1 and 1. That's exactly right. Make the substitution. Make this guy use negative v1, 2. It's going to be negative 1 and 1. Here we go. That's u vector. And of course, let's review what we said previously. The algebraic multiplicity here is 1. The geometric multiplicity is 1. They are both good. Once more, what's the geometric multiplicity? The dimension of the eigen space. Number of vectors. Once more, here we go. That's u2, which is with a negative 4. Similar steps, just substituting, you will have this guy. Also, the ratio exists, so one of them will be eliminated. Very simple. Now I have the first component equal to the second component. I will make the substitution. It's a 1 on 1. Let's check. If these two vectors are perpendicular, are orthogonal, yep. If you multiply the first component, the second component, add them together, you will end up having 0. So u1 dot u2 is equal to 0, which means the dot product of the inner product of these two vectors is equal to 0, which will lead to an orthogonal matrix. Are we right? Once more, these are the eigenvectors. Now and the eigenvalues. Now I will get the model matrix or the B matrix. And also I will put them on a unit matrix. Okay, these are the vectors. I will divide the first vector with its magnitude, the second vector with its magnitude. Just simply it's a coincidence to have the magnitudes equal to each other. That's the U matrix. If you get the transpose. Also, if you multiply them together, the result is going to be a unit matrix, right-hand side equal to the left-hand side. It's beautiful. And then now I can get a similar matrix. Now I can get a similar matrix to the first matrix, which will make it a diagonalizable matrix and do the diagonal form. So once more, this is U transpose, or the inverse, times the A matrix, and that's U matrix. Are you with me? Multiplying them together, you will end up having, just a second, that's U matrix, which is the diagonal matrix. Once more, this method. This matrix is similar to this one. This matrix is similar to this one. Okay? Any problems? Okay, perfect. Let's go for this case. Another problem, other numbers, and also it's symmetric, so it's really very good. And then we need to redo the systems. I will start with finding the quadratic equation. It ends beautifully, but now you have one of the eigenvectors is equal to 0. If one of the eigenvectors values is equal to 0 and the other one is positive, we call this matrix semi-positive definite. Semi-positive definite. So I have positive definite when all the eigenvalues are positive. Positive semi-definite or positive semi-definite when they are positive, but one of them is equal to 0. We call semi-negative definite if one of the eigenvalues is equal to 0, but the other one is negative also. Is any one of them is equal to 0? Am I right? If they have alternative signs, like the problem that we just ended, then we will call it indefinite. Okay? Okay, now once more, let's do some substitutions. I'm evaluating when eta is equal to 0. Once you do the substitution, you will have two identical rows. Similar steps. Now I have u11, can use U1, 2 is equal to 4 if you like. Okay, once more, here is the matrix. I've used the 4. So U1 is negative 3 and 4. Any questions? Any questions? Once more, I will use U2, 25. Making the substitutions, making the dream atoms. It's ended up 4 over 3. I use the series of 4 over 3. Also remark that these two vectors are orthogonal, Mr. Ziad. Are you with me?
Yeah.
So the product also is equal to 0. In a similar manner, that's the matrices. I'm getting the transpose, multiplying them together. You will have the unit matrix. I can get similar matrix to this one. Now, Nada, what's the similar matrix to this matrix? It's going to be 0 and 25. Am I right? The similar matrix. The similar matrix, the diagonal form of this matrix will be 0, 25, 0, 0. Here we go.
Okay. 25 there.
And then eigenvalue was 25. Any problems? Whatsoever, any problems? What's going to be the difference if I have a 3 by 3? Cubic. So I will have how many values and how many vectors? So each one of them, for the evaluation of the eigenvectors, the eigenvalues, I will have a 3 by 3 system. So this system, okay, once more, this system is going to be 3 equations, 3 rows and 3 columns. And also will lead to infinite number of solutions, blah, blah, blah. Okay? Very good. That's the first part of our lecture for today. And those, in order to know the steps, the main steps in how to evaluate your eigenvalues. Now I will have to go to our main slides. Okay? How it is written in the PDFs. I've already sent you the PDFs, all of them, and I believe I sent you this one, or I will send it to you later today, just one. Okay, once more. Let's go through the definition. This is chapter 1, 16. He started with a definition of endomorphism. What's the endomorphism? Let's define it. Okay, let E be a vector space over K. What's K? What's new? K is real or complex numbers. Okay, we call endomorphism. What's the linear transformation that we will call it endomorphism? Okay. Once more, from E to E, it's a general transform, from E to E. To be an example, if null vector U, if there is a vector, it's called U, times alpha equal to A times U. That's the introduction. Alpha is the eigenvalues, U is the eigenvector. So once more, alpha is an eigenvalue for this eigenvector. We use the linear transform here because the matrix that you were dealing with, it's the matrix of the linear transform. Are you with me? So now we are connecting what's happening in eigenvalues of the eigenvectors to the definition of the linear transform. We already talked previously that the A matrix, okay, A times U or A times V, so A times alpha 1, alpha 2, alpha 3, which leads to B1, beta 1, beta 2, the matrix of the ordinary change between vector spaces. Okay, so alpha is the eigenvalue for F. U is the eigenvector for F. Now I know alpha, eigenvalue. U, eigenvector. Okay? Once more, I have A times U equal alpha times U. I'm redoing everything once more. But I'm calling the vector U, which is the eigenvector X. Does it make a difference with you? Now, alpha is the eigenvalue for A and X is the eigenvector of A corresponding to alpha. So instead of having U1 and U2, I will have X1 and X2. Are we right? Are we okay? Then the second step. Look how it is written. Proposition. Let A be a square matrix n by n. In the slides دي يا زياد مهم. It's not the time to discover your fingers or strings of n. Just focus. So now I have A, which belongs to the square matrices. We already saw the square matrices. صح? Okay, let's define. Let alpha be an eigenvalue for A and consider the set. What to the set? n alpha, which is x belongs to the n by 1, is defining the vector space for the eigenvalue space. So now x belongs to the n by 1. Okay, here we go. U belongs to n 1 by 2. So it was 3 by 3, I will have 1 by 3. So for generalization, between 1 to 1 by n. N by 1. Okay, which is a function in k because it may be real or complex, such that ax is equal to alpha x, au is equal to eta u. So now I'm talking about this guy. Okay, once more, m alpha is a subspace of n plus 1. Yes, the vector spaces is like this, it's a subvector space. Then the eigenvectors of A corresponding to the eigenvectors of alpha are the elements of M alpha except 0. We already explained. If this guy is equal to 0, then you will have a trivial solution. Am I right or not? You will be solving A times 0, of course it will equal to alpha times 0. We already answered this. Okay, once more. M by N alpha, blah, 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 blah. Okay, defined. This system, as I showed you in the beginning, with the first slide, it can be multiple matrix. That's the homogeneous system that we were solving. That's the homogeneous system we are solving. Okay, so once more, okay, we call hop geometric multiplicity. Once more, what is the geometric multiplicity? Dimension. Of what? Dimension of the eigenspace. Okay, so he's defining it. Of the eigenvalue alpha, and we symbolize it. Please look to the symbol. Mg. Mg, okay, it is the geometric multiplicity. But remark in Portuguese, they usually change the names. Okay? So it's a geometric multiplicity. Are you with me?
Yes.
Geometric multiplicity. Are you with me, guys? Okay. It's a geometric multiplicity result to the dimension of the subspace of M alpha. Now everything comes beautifully to each other. Now I have M alpha as a subspace of n by 1, and we have the geometric multiplicity is equal to the dimension space. It's equal to the dimension space. Alright? And of course, it will be less than or equal the dimension of all the eigenvectors. And at the worst case scenario, it will be equal to 1. So really, the geometric multiplicity, it must be greater than 1, but less than or equal to n. All coming beautifully. Okay? Once more. Let A in my matrix, alpha eigenvalues. This is the geometric multiplicity. Remark, it's equal to n, the dimension, minus the rank of A minus alpha n. It makes sense. What's the rank here? What was the rank here? So 2 n minus 1, you will have the geometric multiplicity of 1. Keep it in mind. Okay, once more, this is the system. That's how to evaluate. Remark. If I have A to the power of k times x equal alpha k times x, k is the algebraic multiplicity. It's the repetition of the eigenvalues. So once more, it will lead to a quadratic, whatever polynomial to the power of r. You will solve the system and get the results. By the idea, if alpha is an eigenvalue for A and the q, A is equal to 0, makes sense. The quadratic equation or the cubic equation that you are dealing with will equal to 0. Now, alpha, the eigenvalue, I will get it from the system. You know from the beginning that x doesn't equal to 0. All of this are trivial, now you know it. This system has a known solution, f, and only if the system has many infinitely variables. So this is a confirmation that this system, in all times, it all makes sense and it's repeated. It will lead to an infinite number of solutions. Are you with me? Once more, the rank of A minus alpha n is less than n. دايما الرانك لوجيك الرانك بتاع ده لازم يبقى اقل من n لان انت مستخدم ايجن فاليوز والايجن فاليوز force the rank to be less than 2 or how it's going to give you an infinite number of solutions. Makes sense. Okay, once more, this is the characteristic polynomial that we are using. Okay, here's a characteristic polynomial, blah blah blah, solve the system, this is the system, getting the values, determinant, all of this in the beautiful. Now, for the main steps that we already used, first step was using this guy, putting it equal to 0, getting the eigenvalues. That's the characteristic equation. Then the algebraic multiplicity, it is the limitation of the eigenvalues. Are you with me? Any questions? Okay, perfect. Now we call the algebraic multiplicity related to the eigenspace, the geometric multiplicity, and we will symbolize the NG by the idea. The algebraic multiplicity, it's an MA, algebraic multiplicity. Okay? تمام؟ انتوا كلكم تمام؟ فاهم يعني ايه algebraic multiplicity وفاهم يعني geometric؟ Okay, the eigenvalues of a triangular matrix are the diagonal elements. لو انا عندي triangular matrix يبقى الايجنفاليوز بتوعها هيبقوا سهل قوي، لان الايجنفاليوز هيبقوا مين؟ الdiagonal elements. Start from here. That was this example, which is very, very good. Okay, I want to show you how these are the steps taken once more. Okay, let's solve this system. This problem is very important. I want to show you more than one remark about this problem. First of all, that's a system which is 3 by 3. All right. Solving it in an equation form, it's not going to be easy. But this matrix in specific is easier in evaluating the eigenvalues. Why? Can anyone answer me? Why? It's our triangular matrix. So if you try to evaluate the eigenvalues, you will have 2 minus lambda, 1 minus lambda, 1 minus lambda, or 2 minus theta, 1 minus theta, 1 minus theta, all right? Putting the determinant equal to 0. So once you do so, you will have an equation which is 2 minus lambda times 1 minus lambda times 1 minus lambda. Diagonal. Try to evaluate the determinant. Okay? So once more, find the eigenvalues. I will solve this equation, which is simply going to be on this form. 2 minus x, 1 minus x, 1 minus x. Here, the x's are the eigenvalues. Are you okay? Okay. Yes, yet. Let's evaluate the value of this determinant using Sarah's rule. Do you remember Sarah's rule? Underline the elements of the principal diagonal, you will have 2 minus x times 1 minus x to the power of 2. Am I right? So, the root 1. Then 0 times 0 times 0, 1 times 0 times 0, minus. This is 0. 0. 0. So the equation is very, very simple. That's the equation. 2 minus x, 1 minus x to the power of 2, and it's equal to 0. So the eigenvalues are x is equal to 2, and the x is equal to 1. Are we right? Princess now, what is the algebraic multiplicity for each eigenvalue? So MA for 2 is 1, but MA for 1 is equal to 2, because it is repeated how many times? That's what's called an algebraic multiplicity. This sign and we already told those signs at the beginning of the vector spaces. Do you remember this picture? I've already spoke about planes 2, and, or, and stuff like that. Okay, see it? So, at this stage, I knew that the eigenvalues will be 2 and 1 with algebraic multiplicities, keep it in the back of your mind. This algebraic multiplicity, because it is repeated once. But the algebraic multiplicity here is, because it is repeated twice. Amen? Okay. Remark, the algebraic multiplicity of each unit. The algebraic multiplicity of 2 is equal to 1. The algebraic multiplicity of 1 is equal to, please, I beg you, for this part, in your exam, you will have still the head of each question. Choose the correct statement in each of the following. Do you remember? So he will play with you with all of these Okay? Now, let's do to evaluate the eigenspace. So, in similar steps, I will get M sub 2, or the eigenvalue relative to the the eigenvector relative to the eigenvalue 2. So all I have to do is to solve the homogeneous system. But the homogeneous system will be with lambda or eta or x equal to 2. Here it is. X, which is the eigenvector, which belongs to the vectors of 3 by 1, so I'm solving 3 by 3 system. And it will be a minus x, I think, or lambda, I think, or eta, I think. It is eta is equal to. I'm solving for the first. Okay. Once more, let's do the substitution. So I will replace I replace every x by. So it's going to be 0, I believe negative 1, I believe negative 1. Am I right? Okay. That's the first step. That's the system. Leave all of this. That's the matrix that I'm aiming. Okay. Let me do this written from step by step together. Okay? شباب الجزء ده خطر. معلومات اللي فيه كتير وبسيطه زي ما انت شايف سهل، بس معلومات لازم تبقى linked together very good. تعالى نحكي السيستم. طبعا انا بعمله كده. السيستم في ثانيه. هي فين الماتريكس يا رب؟ فين الماتريكس؟ ماتريكس اهو هعمل اوجمنتد ماتريكس. اوكي؟ هيبقى 2 minus 2 كام؟ 0. وده بزيرو وده بزيرو. 0. 1 minus 2 negative 1 and 1. 0. 0 and negative 1. The system origin 1 with 0 0. Try to get the reduced additional form. Try to get the reduced additional form. The reduced additional form, how it's gonna be? I will multiply the elements. Oh, first of all, I will replace the second row by the first row. So it will be 0, am I right? 1, negative 1, and 0. Yes? I've already changed it and multiplied it negative. And I will take the first row to be the last row. Are you with me? And I will move the second row to be the third row to be the second. So it's going to be 0, 0, 1, and 0. Are we okay? So, this is the reduced addition form. What's the remaining step? To add the second row to the first row. If I added the second row to the first row, guys, I will have 0, 0, 1. 0, 1 and 0. 0, 0, 0, 0, 0, 0. So, now I'm getting U1. I will use my symbols, then I will use their symbols. So I'm getting U1. Can you remind me what are the elements of U1? Never. What are the components that we used to use? The first vector, first component, alright? The first vector, the first vector, third component. So, is it going to make a difference if I hold this guy X and this is A, B, and C? This is A, B, and C. So let's evaluate together. The first row. 0 times A, 1 times B, equal. Let's do the second row. 0 times A, 0 times B, and then C is equal to. Did I said in relation about A? Use this value and substitute. So it's going to be the X vector, which is going to be A, 0, and 0. So, now I can take A as a common. Am I right? So it's going to come up to A times 1, 0, and 0. Am I right? So the eigenvector 1, this is X, is going to equal to the basis of this eigenspace is going to be 1, 0, and 0. Is it clear? Never, okay? Okay. انت معايا هنا 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 صح؟ اكسلنت خليهم بقى معدل. ما هو ده يفرق نمبر سولوشنز ولا انا غلطان؟ مش انت بادئه ب 3 النص؟ عندك الرانك كام بكام؟ صح؟ 3 minus 2 يعني الاي سبيسيفاي بكام؟ 1 دايمنشن. طيب هل انفك 0 times A 1 times B 0 times C equals 0 يعني دي كده دي بتساوي كام؟ اكسلنت السكند رو يعني 0 times A 0 times B 1 times C is equal to في هنا ايه؟ في حاجه ثانيه؟ يبقى ده الفيكتور دي الفيرست كومبوننت زي ما هي. السكند كومبوننت اللي هي بي بكام؟ اللي بعدين بكام؟ صح؟ يعني دلوقتي اقدر اخد U1 sub 1 يبقى 1 و 0 0 am I right؟ يعني اذا الايجن سبيس بتاع الايجن فيكتور رقم 1 هو عباره عن البيزس اللي الفيكتور بتاعها بكام؟ ده يا زياد انت معايا؟ قشطه اهو A minus 2IX that's the system we are solving. I will try to reach with a draw operation the reduced echelon form. Reduce the echelon form. B is equal to C to 0, C is equal to 0. يبقى إذا لما أحط B 0 C 0 أصبح A 0 0. هو اللي المستوى تيك إيه يا كومن؟ يبقى البيزس بتاع ده بيطلع بكام؟ البيزس بتاع ده هو 0 صح؟ أوكي. Remark. We conclude that the geometric multiplicity بتاعت ال 2 طلع بكام؟